Hello, pre-calculus students. This is your last week of notes and assignments. So congratulations. So we are doing limits. Last week we did limits graphically. This week we're going to do it analytically. And so we're going to look at the constant function, f of x equals 3. And for some reason, as simple as this function is, it confuses people because they don't think of it as a function. So to the right, I've graphed y equals 3, which is f of x equals 3, and it's just a horizontal line. And so let's take a look. We're taking the limit as x approaches -1. So where is that? -1 is right. Oh, I just realized I'm not going to be able to graph that or write on it because this is a separate thing. So -1's right here. So as I approach -1 from the left, what does the y value of this function get close to? Well, obviously it's 3 because it's constantly 3. As I approach -1 from the right, what's the y value of this function close to? Not even close to, it is 3. Clearly, as you approach from both sides, the function is going to get close to 3. So that limit would be 3. Hopefully it's painfully clear. The limit of a constant will always be the same value. Now I've rewritten it. Instead of putting f of x here, I put 3. When you see 3, that just means y equals 3 or f of x equals 3. It's a constant of a horizontal line, or it is a horizontal line, the graph of it. So this one here, the limit as x approaches 1. Well, here's 1. As you approach from the left and right, it's a constant. It's going to be 3. That answer's going to be 3. So the limit of any constant is always going to be that constant. And so this is actually going to be a property that we're going to look at. There's many properties. So to generalize this, the limit as x approaches a could be any value of x, of a constant c. So c is a constant function. That limit will always be c. Whatever this constant is, everywhere, the limit will be that constant. So that's why we have that. So that's the first concept you have to get. The limit of any constant will always be that constant. Now the next is the limit of y equals x. f of x equals x is the function y equals x. And I have it drawn to the right here. So this is y equals x. And so looking at this, we're taking the limit as x approaches 2. Well, I'm going to circle 2. We're going to approach from the left and the right and see what happens. As I approach from the left, clearly the function gets very, very, very close to 2. As I approach from the right, clearly the y value of the function gets really, really close to 2. So if I approach 2 on the x, excuse me, as I approach 2 from the x, the y is going to get close to 2. So this answer will be 2. Now let's look at -2. There's -2. I'm going to approach from both sides. So if I approach from the left, what does the y value get close to? -2. As I approach from the right, what does the y value get really close to? -2. So clearly this limit is -2. This should be making sense. Since y equals x, whatever x gets close to, y is going to get close to. So the last one, take a look. I'll let you think about the answer on example 3. You can pause if you want to before I give you the answer. Clearly, it's going to be 0. Because whatever x approaches, y approaches because y is x. So that's another property that you have to know. So the generalization of this, I'll write it down. the limit as x approaches any number a of the function y equals x will be a. Excuse me. So that's another property. Using these two properties and a bunch of new ones I'm about to show you, you will be able to find the limits of a bunch of things. So let's look at all these properties. So a few things they point out. A, K, A, and B are all real numbers. F and G are functions. The limit of f of x as x approaches a is a, and the limit of g of x as x approaches a is b. And some more prerequisites. For limits that exist and are finite, the properties are demonstrated below. So let's take a look at this. This one here, I already showed you. It's a constant. The function always equals k. So as x approaches a, you'll always get closer to or equal to a. Excuse me. Now this next one is a new property. So you have a constant times a function. Well, basically it's saying if you have a constant, you're able to, in a sense, just factor it out. So this constant k can come out in front, and that's what happens. So therefore, you take the limit of your function, and we know that's a, so it's going to be k times this limit. So anytime you see a constant, you are allowed to pull that out. And I guess I could show you example to the side. We'll do, ooh, that's kind of fat. Let me shrink that down. The limit as x approaches, I'll do something real basic. X approaches 3 of 4x. Well, you should notice that 4 is a constant. It's the k I have here. So I'm allowed to pull that 4 out in front, and I get the limit as x approaches 3 of x. Well, this limit, you should know, we did that up above. That's the limit of y equals x. And that limit is whatever x is approaching. So if x approaches 2, the limit's 2. X approaches -2, the limit's -2. X approaches 0, the limit's 0. And we had it summarized. We don't. I lied to you. I summarized it for you right here. So if you have the function y equals x, as x approaches a, it's going to be a. And hopefully you remember that from this graph. Whatever x gets close to, y gets close to, because x and y are the same. So looking at this, we have the 4 that we just copy, and the limit as x approaches 3 of x is just going to be 3, so we're going to get 12. That's what's going on there. The next two are the sum and difference functions. So you have a limit of two functions being added. All they're saying is you can take the limit of the first function and you can take the limit of the second function separately and add those two limits together. Similarly for subtraction, you take the limits individually and then subtract. Similarly for multiplication, you take the limits separately, then you multiply. And similarly with division, you take the limit of the numerator, you take the limit of the denominator, and the limit is the limit of the top divided by the limit of the bottom, as long as the bottom's not 0, because if the bottom's 0, that's undefined, and there is no limit. Or the top could be 0 too, and that's going to be indeterminate, but we'll talk about that later. So here's another example. I should do at least 1 or 2 examples for the above. I will, just a very simple one. So these two, I'll just use one example. It's going to be this pretty similar. the limit as x approaches -1, and we will do x plus 3. Well, what this property is saying, okay, first you have to recognize there's two functions there. That's one function, y equals x, and that's a second function, y equals 3. So this is like f of x and g of x. This is f of x, this is g of x, just like here, f of x plus g of x. Well, it says I can separate these out and take the limits separately. So what I can do is take the limit of the first one plus the limit of the second one. Well, the limit of the first one, it's a y equals x. That's just going to be -1. The limit of the second one is a constant. We talked about that earlier, so that's going to be 3. So this will be 2 for that one. All right, let me do a couple more examples for you. I will do the limit of a product. Let me erase that. So say you have the limit as x approaches 2, and we will do a product of two functions. We will do x squared times 2x. Ooh, I can't do that yet because I haven't taught you that. So let me back up. I should have thought this out better. I should have. Okay, I'm going to do something that seems weird. There are two functions. I know you can multiply them, put it together, and make it one function, but we're just going to keep them separate. So the first one, that's like my f of x. The second one is like my g of x. So that's like g of x and f of x. I have the limit of two functions being multiplied. I have the limit of two functions being multiplied. To make it look even more similar, I will do that for you. Well, this rule says I can take the limit of each individual function and just multiply them together. So this will be the limit as x approaches 2 of x times the limit as x approaches 2 of 2x. Well, I'm going to apply another rule. Well, the first one we learned earlier, the limit of y equals x is just going to be what x approaches. That's going to be 2. The second one, it's a constant times x. So what's the rule for a constant? We learned you're allowed to take the constant out front and multiply that by the limit of the function. Well, the limit of x as x approaches 2 is going to be 2. So that answer is just going to be 8. So that's using the product rule. If you have a limit of a product, it's the product of the individual limits. So that's your next rule. And I need some space, so let me get rid of all this. So the next example, we shall do 2x. Oh, I'm going to be, yeah, we'll be okay. Why did I put infinity? Am I nutso? I think I'm nutso. Let's do 1. Now again, because you don't have a large set of functions you're able to do the limit of, I have to do some simple ones. And you're going to say, well, won't the x's just cancel? Yes, they would. But assuming we didn't notice that, the rule says I can take the limit of the top and the limit of the bottom and divide them. So the limit of a quotient is a quotient of the limits. Well, I know on the top I'm able to factor out a constant. And what I'm going to get? The constant times the limit, which is 1, and the limit of the bottom, which is 1, so the answer is going to be 2. So that's an example of the quotient rule. Now when the denominator is 0, we'll have to deal with that I think it's the next lesson, maybe it's the end of this one, I can't remember. So we have 3 more rules to go. What is the next one saying? I have a function being raised to a power. And they're saying that power is any positive integer. How do you find that limit? Well, it says you take the limit of the inside first and then raise it to that power. So let's try this one. I'll do it with something very basic because you don't have a lot of things we can do. I'll take the limit, whoopsies, as x approaches 2, we'll keep them simple, and we'll say x cubed. Well, here's the rule. I have the limit of a function to a power. It says I can take the limit of the function and raise that whole thing to the power. Well, that function, limit of that function on the inside is going to be 2 cubed, so I'm going to get 8. Now, another way to do this exact same problem is to rewrite it. I could have said that this is x times x times x. And then I could have done the product rule and take the limit of each one individually. And each individual limit is 2, and then multiply together and get 8. That would be a pain, but it is following the rules that we have. Now, there are some shortcuts. Some of you might be seeing them already and saying, why are we being so tedious? It's important that you know these rules because you're going to apply them to different situations. And some of the shortcuts are implying things that we don't know yet, especially continuity. Once you learn continuity, it's going to open up and make limits so much easier. But right now, we don't have that. So that's limits of exponents. The next one, okay, the next one's very similar. So instead of an exponent of a positive integer, we can rewrite this. Let me just show you something. This limit here is the same as the limit as x approaches a of f of x to the 1 over n power. That's how a root works. So you have the 1 over n power. So basically these are very similar, and it's going to have a similar process. You take the limit of the inside function first, and then you take the root after. So I'll do an example. I just don't want to make this video too long, but I think it's better if you guys see examples. So let's do this. The limit as x approaches, I'll do different, 4 of the square root of x. So we have a root, limit of a root. What does the rule say? I take the limit of the inside function and then take the root after I take the limit of the inside function. Well, this equals, the limit of the inside function is 4, the square root of 4 is 2. Now again, some of you might be seeing some shortcuts, and here's the problem. We have building blocks. We're building up from either given definitions or theorems or previous postulates. So you can't just say, oh, I see a shortcut, I see a pattern, I'm just going to use that pattern. Everything has to be verified and proved that it is consistent and it works, and therefore you have to build from the basic building blocks. So there are a lot of shortcuts that I'm not telling you, but it's for a reason. Sometimes people jump to conclusions and apply wrong things in math because they see a pattern, but they cannot prove it through theorems, definitions, and postulates. So it's important that you understand the basic principles. When you get to calculus, you have to understand why you do the things you do, because the questions get very intricate, very abstract, and if you don't understand the basic principles and the reasoning and logic and what's required for one of these properties to work, you can get into big trouble. And it's what happens to a lot of calculus students. They just kind of do things the way they did without really understanding fully, and it causes much pain. So this last one, I think it'll make you feel better. This is kind of what I was talking about. This is a shortcut application. So polynomial function, p of x, given right here, we're assuming that's a polynomial function. I don't think we were told that above. Actually, they should have told you that somewhere, but they didn't. So basically, here's what's happening. They're saying if you have a polynomial function, well, for example, the x plus 3 we had here, that's a polynomial function. This is 2x squared. Basically, it's a polynomial function. So here's the last one. This is the last property. If you have a polynomial, to find the limit, you wouldn't have to break it down into small pieces like we did earlier. All you do is plug in a. So the value at a is the same as the limit. I'll give you an example of this one. And this property, I don't want you to use for the worksheet quite yet. I want you to practice the properties. So I actually shouldn't be showing you this, but I ask of you, don't use this property yet. You're going to do some very tedious things, but it's going to force you to know the basic properties of limits that a lot of people kind of forget because they use shortcuts or they use theorems before they're ready. The limit as x approaches 2 of 3x squared plus 2x minus 1. I'm going to show you the long way and the short way. So the long way is you have a sum and a difference. So one of the properties we have are the sum and difference properties. This one here and this one here. So technically we could rewrite this as 3 separate limits. Wow, I'm going to get really tedious on you just to show you exactly how we use the properties we're given correctly. So now, wow, I have a constant here. I have a constant rule where I'm allowed to pull the constant out in front. Now, I'm driving some of you nuts because you just want to go to the shortcut. Sorry. We have a constant here. I have a constant rule that says I'm allowed to pull the constant out in front. And this last limit, it's a constant function, so we know that's 1. Now, another rule. We have a power here. That was this one. If you have a function raised to an exponent, you take the limit of the inside, and then you raise to the power. So I need to rewrite this as 3, and then the limit as x approaches 2 of x, and then I square it. So I take the limit of the function inside, then I square it, and then, well, this limit here, we've done a few times. We should know that's 2. And then I have 3. The limit inside that is going to be 2 inside the bracket squared. And then I'm going to get 3 times 4. 3 times 4. I'm on drugs, I think. Just kidding. 3 times 4. So 12 plus 4 minus 1. That's 6. I hope that's 15. I hope. Ooh, that's an ugly 15. Sorry. All right. So that's the long way. That's the tedious way. That's the way that you would say, why do I have to do all that? Just let me use the shortcut. I don't want you to use this rule because I want you to be driven so crazy by the long way I just did that it'll be ingrained in your brain, the basic properties of limits. So here is using this property. And again, for this lesson, please do not use this. You're going to hate me. Sorry, but that's the way it is. Here is the shortcut that you're not going to use for this lesson. Not going to use. Okay, so this is a polynomial. To find the limit of the polynomial, you just plug a into the polynomial. So, yeah. Yeah, this is so much easier. That's it. That's how you find the limit of a polynomial. So, I don't know, on the assignment it gets pretty long. I want you not to use that. Maybe if you have a polynomial in another function, I'll let you use that rule. But if you just have only a polynomial, I just encourage you, just try to make sure you have these properties down before you go right to the polynomial rule that I just used here. And I know this video is getting long, and we have another video to go through, but I'm going to introduce to you. No, I'm not. No. I don't want to keep getting longer. So I have a couple of examples. 4 examples. So I'm just going to do these, but you should try each one. Pause this video, try the first one, and then see my explanation, and so on and so forth for these. So I'm going to go right to it, but you should pause and try it on your own. So the first one, I have a a sum. So I'm going to break them up into 2 individual limits. Because really, the only limits that you know were those first 2 that I showed you. The limit of a constant and the limit of x, y equals x. Those are the only 2 limits that you know that I'm giving to you. Now, you will know when you get to calculus a bunch more that you can figure out right away. But those are the only 2. And then you have all these properties. So using those 2 limits and these properties, you're able to find all these limits that we've done. So technically, you don't know the limit of 2x plus 3. You have to use the properties to break it down because you only know the limit of a constant and the limit of y equals x. Now, if you use the polynomial function rule, then you could do this quickly, but we're going to do this a long way. So here we have a constant. We're going to use a constant property where I can pull the constant out in front. And then we know this limit is 2, and this limit is 3. And so we have the answer 7. So here's example 2. You can go ahead and pause and try this on your own. But here we go. So I have sum and difference properties. So I'm going to break this up into 3 separate limits. Now this first one, I have a function to an exponent. So the rule says I can take the limit of the inside function and then raise it to the power. The second one, I have a constant. I'm going to pull it out in front. And the third one, we know that's 3. We know the limit on the inside is 1. And we pull the constant 4. The limit of x we know is 1. And we get 1 minus 4 plus 3. And that's 0. All right. Next example. Okay, this is the one. I'll let you use the polynomial rule on the inside since it's not a straight polynomial. So go ahead and pause and try this, and then you'll see my example. Okay, so what's going on here? I have a function inside of a square root. So that property we saw earlier, I am allowed to take the limit of the inside and then square root it. Now I'm going to allow you to use the polynomial property. So to find the limit of that polynomial, all I do is plug in -2 into the polynomial. So I'm going to get 8 plus 8, which is 16, and the answer is 4. And here's a quotient rule one. So go ahead and pause and try this on your own. So you would take the limit of the top separately from the bottom. Whoopsie daisies. That's not what I wanted to do. There we go. Sorry for the ugliness. Okay, so the top one I am going to break it down to another stage. So we have a function raised to a power. Using the power rule, I'm able to take the limit of the inside function and then raise it to the power. And the limit of the bottom, so I'm going to tell you with cosine and sine, it's same as the polynomial rule. I didn't want to get into this. You have to understand continuity to understand when you can plug in the number to find the limit. But I'll just say this for now. Cosines and sines, to find the limit, you just plug in the number that x is approaching, and that will be the limit. So when you get to calculus again, you'll learn more about all the trig functions. But for today, just whenever you have a trig function for your homework, just go ahead and plug it in. So on top, I have a polynomial here. So I'll let you use the polynomial rule. Oh, the bottom I didn't plug it in. So we are going to get 3 times 0 squared minus 2 times 0 plus 3, whoopsie daisies, squared. And the cosine of 0 is 1. The top is going to be 3 squared over 1. The answer is going to be 9. So that is an example using all the properties. Wow, sorry this video is getting really long. Okay, piecewise functions. It's important when you get to calculus, piecewise functions you will see all the time. Multiple choice and FRQs. You have to understand them. They need to make sense to you. So first I'm going to show you how to graph piecewise functions. I said draw, but I should have said graph. So I have a piecewise function here. So I am going to do each part in a different color than explain. So this one I'll do in blue. So this is a function. It's y equals 1/2 x plus 5. So I'm going to graph that. We have a y-intercept of 5. 1, 2, 3, 4, 5. And we have a slope of 1/2. So I'm going to draw a line with a slope of 1/2 through that point. I didn't want pink. I thought I had, or I wanted blue. Can't I change it? Oh no. Oh my. Okay. Hopefully that's right. Whoops. Whoopsie, whoopsie, whoopsie. Is that? It's pretty close. Pretty close. It's off a tad bit. I think that's better. Yeah, that's pretty good. Let me see. 1, 2, 3, 4, 5, 1. It's pretty close. Pretty close. Pretty. Whoa, 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 whoa. Whoa. Oh, wow. That's sad. 2, 3, 4, 5. Let's try this again. Okay. That should be pretty good. Oh, no, I should have drawn it with a... Okay. It's okay. I have to calm down. We're going to be okay. The next one, let's do with red. This will be red. And the equation y equals x squared. I'm going to have to freehand this. Freehand it. This might be actually better. 0, 0, 1, 1, 2, 4, 3, 9. Yeah, I should have freehanded the line. This is not going to be pretty, sorry, my friends. Yucca. Close enough. That's beautiful. And then I have the last one. I will do that in green. And that's y equals 1 over x. So I'm just going to show you the graph of this. That one also is going to go through that point. 1, 1. And you know what? I'm going to do a rough graph. It's not going to be perfect, but you'll get the idea. It's going to have a vertical asymptote and a horizontal asymptote. Whoa. Yeah. Beautiful. And it's going to have the same thing on the other side. Ooh. Yeah, that's beautiful. Okay, so I graphed each of these 3 functions. Now let's understand what the piecewise function is doing. This first graph here only exists from -infinity to -2. It stops at -2. So I have this going for a lot longer. Wow, I am struggling. It needs to stop at -2. So I have to stop right there. It only exists to the left of -2, and I want to make this a single-sided line. Can I do that? Oh no, I am sad. Okay, I'm going to redraw this line because it doesn't keep going to the right. So therefore, I'm going to delete this and only draw it in one direction. Yeah. And not only that, I want you to realize at -2, this function doesn't exist at -2 because we have a less than no equals. So at negative 2, this graph doesn't exist. So what I'm going to do at that point, I'm going to draw an open circle because that function doesn't exist at that point. Let me do that. And so this will be non-existent. Whoa! Yoshida is blowing it. This is proof that you shouldn't do drugs, kids. Just kidding. I'm going to get myself in trouble for joking around. Okay, there we go. So maybe this time I have it right. So that line only exists from negative infinity to negative 2. At negative 2, there's no equal sign. So you have to put a hollow open dot because that graph doesn't exist at that point. Okay, so that's what's going on with that. Now let's take a look. This red graph only exists between negative 2 and 1. That's what this means. So to the left of negative 2, it doesn't exist. So I need to erase to the left of negative 2. I have to stop right there. But you'll notice there's an equal sign. This graph exists at negative 2, so I do want to color in at negative 2. It exists there. And then at 1, you notice this graph is defined for x equals 1, and it stops at 1, so I don't want anything past 1, so I want to get rid of anything to the right of 1. But it does exist at 1, so I want to color that in there. Okay, so my parabola x squared goes from negative 2 to 1, and that's where it exists, between those x values, nowhere else. And then to the right of 1, from 1 to infinity, ooh, that's bad. I can't erase that either. It's not a double less than sign. And it shouldn't be equals. Oh, that shouldn't be there. You can't equal infinity, so you can't have the equals there. So from 1 to infinity, not including 1, it looks like 1 over x. So what does that mean? Anything to the left of 1 doesn't exist. So I'm going to erase everything to the left of 1. Bammo. And then there's going to be a circle at negative 1. Let's get rid of that piece. So that is a piecewise function, how to draw one. Now, finding the limit of a piecewise function, well, technically, you could look at your graph and do it graphically, but you should be able to do it analytically also. So I will show you analytically, and we'll use our shortcuts in this. So part B, finding the limit. Now, finding the limit at any point that's not negative 2 and 1 is easy. I'll go ahead and do one. I'll do a few. This video is going to be really long, and we have another one. Sorry. The limit as x approaches negative 4. So where is negative 4? It's right here. So which function would you use? The blue one. How do you know the blue one? Because negative 4 is between negative infinity and negative 2. So you would use this. So to find this limit of f of x, you would take the limit as x approaches negative 4 of 1/2 x plus 5. You plug in. Now, that's a polynomial. So we learned if you have a polynomial, to find the limit, you just plug in the number. And that's going to be negative 2 plus 5, which is 3. There we go. That one's not bad. So Here's the next one. We will do the limit as x approaches 1. When you find yourself at the intersection of two of the separate graphs of a piecewise function. Now, assuming you don't have the graph, okay? So looking at the graph, clearly you could see the first answer, but we're going to assume the things I'm doing right now, you don't have the graph. You're just finding the limit. So for the first one, you see, oh, -4. Where's the graph -4? -4 is between these, so it's always this function. But now we're at 1, and you should notice 1 is at the intersection of x squared and 1 over x. So how do you find the limit when there's two different functions involved and you don't have this graph here? Assume you don't have that. We're going to do this analytically, not graphically. So you have to use your properties of limits. For this limit to exist, you have to find the limit as x approaches 1 from the left of f of x, and you have to find the limit as x approaches 1 from the right of f of x. So if you want to find the limit as x approaches 1 from the left, where is the function left of 1? Well, here's 1. X is smaller than 1. Smaller is left of. So you would use the x squared. And then you're approaching 1 from the right. Well, to the right of 1 is bigger than 1. So which function exists when x is bigger than 1? Right here. When x is greater than 1, I use 1 over x. So this would be the limit as x approaches 1 from the right of 1 over x. So this first one, we would use the power rule, or this is a polynomial. So we're just going to approach 1. So that's just 1 squared, or 1. Here we're going to use the quotient rule. The limit of the top is 1. The limit of the bottom is 1, so we get 1. Now last week we learned if the limit from the left and the limit from the right are the same, that is the limit. So the answer to this question is 1. So when you have a piecewise function and you're finding the limit where two functions intersect, you have to find the left-hand limit and the right-hand limit separately. If they're the same, that is the limit. If they are different, the limit does not exist. So that is piecewise functions. All right, we have more. It never ends. This is a very long video. I think I'm missing some examples here. Maybe not. Okay, I don't think I'm missing some. It's going to be on the next one, hopefully. Hopefully. I hope I didn't miss some. If I did, I might have to have a third video. All right, so intermediate forms. What does that mean? So for this first one, I'm going to show you something very bad you shouldn't do. So you have this rule. We have a polynomial divided by a polynomial, and it's a quotient. So you have the quotient rule. You're allowed to take the limit of the top and the limit of the bottom separately. So I'm going to write this as the limit as x approaches 2 of x squared minus 4 over the limit as x approaches 2 of x minus 2. Then you learned you could just plug this in here, and that would get you 0. And you learned if it's a polynomial, you can plug that in there, and that will get you 0. And you have 0 over 0. Now, some of you may say, that's undefined. I learned you can never divide by 0. And then some of you might say, well, that equals 1 because it's the same thing on top and bottom. But technically, that's undefined if it equals 0 over 0. But it does not equal 0 over 0. It approaches 0 over 0, but it doesn't equal. And so this is where it gets confusing. If you end up with 0 over 0 in a limit, it's called an indeterminate form. You should never say it equals this. That's not true. That is bad English in math. It's wrong because this is undefined. So you don't know if this is undefined. It might be undefined. It might be a constant. It might be infinity. You don't know. Infinities are weird and zeros are weird. So don't write it that way. That's muy mal, very bad. So you shouldn't do that. So I'm going to show you what you do. So if you get a limit and it's in the form of 0 over 0, you have a problem because that limit could exist and it might not. So what do? Here is the secret. You have to try to rewrite the function differently. You have to rewrite it in a way that you don't get 0 over 0 or infinity over infinity. So that's your secret, rewriting. Now, further on in calculus, you're going to learn L'Hopital's and other ways to deal with these situations. But right now, you're going to learn something else. You're going to have to use your algebra skills to write this in a new way that magically makes it work. So in the first example, we're going to factor and cancel. Okay? Factor and cancel. The top factors nicely. X minus 2, x plus 2. And those will cancel out, leaving us with the limit as x approaches 2 of x plus 2 over 1. This is very simple. We have a polynomial, plug in 2, the limit's 4, and we are done. Now, some of you might say, I changed the problem. Technically, this original is not the same as that. Technically, x cannot equal 2. Because if x equals 2 in the original function, you're dividing by 0, and you are undefined at 2. But remember the limit? The limit, x never reaches 2. It gets really, really close to 2, but the limit doesn't care what happens at 2, doesn't know what happens at 2, it just knows what happens close to 2. So it never reaches 2. So when I take the limit of this, it never gets to 2. So I don't have to worry about the 0 in the denominator. So that's what's going on there. So you have to rewrite it. Now the second one, you can factor actually. I'll show you that. But I will show you the other way. So for the second one, somehow you have to write it differently. You have to write it in a way where you can find the limit. And here's the secret. You're going to rationalize the radical part. Now, prior to calculus, you're always told you're not allowed to have radicals in the denominator. You just can't. I don't know why. It's a rule. Because in calculus, you're allowed to have radicals in the denominator. And you don't have to simplify that. But in this case, this radical, so you plug in 4, you get 2 minus 2, that's 0. 4 minus 4 is 0. You get a 0 over 0, which is called what? Yes, intermediate form. Indeterminate form. You're not able to determine that limit. And I'll show you an example why it's not undefined later. Probably next video. So for this one, you're going to multiply the conjugate of the radical part. So you learned in Algebra 1 that, actually you learned this in 3rd grade. Anything times 1 is itself. You can multiply by 1 and it doesn't change anything. So I'm going to multiply this whole thing by 1, but that seems silly, right? My 1 is going to look different than that one. My 1 is going to be a special one. It's special. Now, I want to point out, on this first one, we factored and canceled. So basically, you want to get in factored form, and you want something to cancel. Because this denominator canceled, now the bottom's no longer 0. So we're happy. So we kind of want to always leave things in factored form to see if something would cancel. But my 1 is different. I'm going to rewrite 1 as radical x plus 2 over radical x plus 2, because anything divided by itself is 1. So since I'm multiplying by 1, as you learned in 3rd grade, multiplying by 1 does not change anything. So these two are equivalent. So I'm going to do the limit as x approaches 4. So the top, we are going to distribute the radical x to both. And I'm going to get x minus or plus 2 radical x. Then I'm going to distribute, oh, I should have done that in green, the negative 2 to both these. So I'm going to get minus 2 radical x minus 4. So you should have recognized this as like a difference of 2 squares. And whenever you have a plus and a minus, those middle terms are going to cancel out. That's why you multiply with the minus and the plus. The middle terms will be canceled, and you eliminate the square root. That's why that works. It's like a difference of 2 square type thing. The bottom, a lot of people are tempted to multiply the bottom out. But like I said in the first one, you want to get things factored and canceled. So you don't want to multiply the bottom out. Whoa, bad color. You don't want to multiply. You want to leave the bottom factored. X minus 4, radical x plus 2. But look, on top we're left with x minus 4. I'll just rewrite this. I know this video is long. We'll just make it longer. You think you are suffering through this long video? I had to make this long video. Look, how nice. Those x minus 4s cancel. I'm left with a 1 there and there. I'm going to use my quotient property that we learned in the previous section. The limit of the top is a constant, so it's 1. The limit on the bottom, so I could take the limit of the inside, then square root it. So the limit of x is going to be 4, because I'm approaching 4. Square root of 4 is 2. I end up with 2 plus 2. Whoa, that's ugly. 2 plus 2, and that's going to equal 1/4. So that's what you do when you deal with radicals. Now, I'm going to do something radical here. I'm going to show you something that's much faster in this case. Some of you are going to see it, and you're going to be fine. For those of you who do the Xbox, I don't know, you still might be able to do it. I'm not too familiar exactly how the Xbox works. But I'm going to factor the denominator. You can look at that. You can't factor that. It's an x, not an x squared. Well, yes, I can. This is the difference of 2 squares. It's going to be radical x minus 2, radical x plus 2. You don't believe me, eh? What's radical x times radical x? X. What's negative 2 times positive 2? Negative 4. Nice. You can say, but what about those other 2 that you neglected? Well, what is, whoops, 2 times radical x? That's 2 radical x. What about these two? Negative 2 times radical, that's minus 2 radical x. They're going to cancel out. So that is factored correctly. That is correct. So, whoa, that was bad. Now, these will cancel, and you quickly get your answer of 1/4. So that's another way you can do it. It's a factoring and canceling method. All right? So let's go to the third example. If you want to try this on your own and pause this, you may. All right. So for this one, we're not going to use the factoring and canceling because it doesn't work on this one. But we're going to rationalize the numerator. We're going to multiply by 1. But you should know what that 1 looks like, hopefully. My 1 is going to be radical x plus 2 plus 2. That's my one. All right. That's like the conjugate. That's like what's going to happen when I multiply the numerator, the radicals will disappear because the minus and the plus. So let me color code this nicely. That. I will do that. Oh, I shouldn't do that color. I should go back to blue on that. This video is really long. Sorry. Really long. So you multiply the first two, you're going to get x plus 2 because the radicals cancel. And then you're going to get 2 radical x plus 2. Then I'm going to distribute the negative 2 to both those. Minus 2 radical x plus 2 and minus 4. And again, do not multiply the bottom because our goal has been to get things in factored form so something will cancel. So I'm going to get the x minus 2 and the radical x plus 2 plus 2. Well, on top, nicely again, because I multiplied by the correct thing, those cancel. Let me rewrite this. I'm going to get the limit as x approaches 2 on top. It simplifies to x minus 2. On the bottom, I have x minus 2, and then radical x plus 2 plus 2. Nicely, these cancel magically, and now I can find the limit. Well, the top's a constant, so the limit of top is 1. The bottom, I could take the limit of the inside part and then square root it. That was a property we learned. So the limit of x plus 2 as x approaches 2 will be 4. So that'll be radical 4 plus 2, which is 1 over 2 plus 2, which is 1/4. So there's another example of what to do when you have radicals in a fraction. And it's called an indeterminate form. Oh, I forgot to tell. Oh, man. Example 2, if we were to plug in 4 here, we'd get 2 minus 2, which is 0. 4 here, 4 minus 4 is 0. That's 0 over 0, which is indeterminate. So therefore, we need to go to a new strategy. And the same thing for example 3. If I plug in 2 here, I get 4. Square root of 4 is 2 minus 2 is 0. So the limit of the numerator is 0, and the limit of the denominator is 0. So these were all examples of indeterminate form and some of the shortcuts that I need to do to make it work out correctly. That's it for the video. Thank you for hanging in there. Yeah, I have to make one more. So there will be a second follow-up video to the second video. So I guess that's the third video. Bye.